Hi, this is Laura Sminsky with Edina High School, and today we're going to be looking at section 10.2, which is modeling and simple rational functions. The first objective is going to be I can model a real-world situation with f of x equals a over x minus h plus k, and then the second one is to go back to what we did yesterday. I can graph f of x equals a over x, and we're going to add one twist. Because the second objective follows from what we did yesterday, I'm actually going to flip to the back side of this worksheet first and talk about graphing a over x. Okay, so if you can find that, that'd be great. So this is more graphing. Yesterday we didn't think about f of x equals a over x for negative values. So we talked about what if a is greater than 0 and what if a is less than 0. Today we're going to look at it if a is negative. So we're going to fill in the table for g of x equals negative 1 over x and sketch that graph. So if I do 1 over negative 4, I get, negative. So we're doing g of x equals negative 1 over x. So if I do a negative 1 divided by negative 4, I get positive 1/4, which is 0.25. Negative divided by negative is positive 1. Negative divided by negative 1/2 is positive 2. So again, we're just plugging values in like we did yesterday. We can see that this is the parent function that's graphed here. This is f of x equals 1 over x. We have not shifted at all, so we're going to keep our asymptotes the same. But now we're going to plot a point at negative 4, positive 0.25, negative 1, positive 1, and negative 1/2, positive 2. And what we can see by doing this is it actually makes it so we have a piece of this graph in quadrant 2, which is different than yesterday. The other half of the graph, it says go over positive 1/2 down 2, over 1 down 1, and over 4 down 0.25. So again, when we do this, when we had a negative x, we can see that we flipped it, a negative 1 over x, we flip it into quadrants 2 and 4. So what's the same and what's different about 1 over x and negative 1 over x? It's the same shape. So the shape is the same, but g of x equals negative 1 over x is in quadrants 2 and 4 instead of quadrants 1 and 2 like f of x when it's just 1 over x. So that was the last thing that we wanted to talk about, and that is that if you make it a negative 1 over x, it switches the quadrants that it's in. So if we put everything together, we can play this matching game in the next situation. We're looking at 4 different functions at the bottom. And so if I look at graph A, I'm going to label these A, B, C, and D. I know that it's in quadrants 1 and 3, which means that it must be positive. So we're either looking at g of x or j of x. And then the other piece I see is that it pushes away from, so remember the original would have been kind of down through here, and it stretches away from the asymptotes, which is when we said a was greater than 1. So since g of x is 3 over x, this one would be g of x. I'm just going to quickly find the next one that is in quadrants 1 and 3, which is letter C, because we're playing a matching game. And again, compared to the original 1 over x, it compresses towards the asymptotes. So I'm looking for, again, the positive one, but in this case, a is less than 1. So that's why letter C would be j of x. Okay, and so then B and D both fall in quadrants 2 and 4, which means that I should have 2 negative functions left, which I do. I'm looking at either f or h. And once again, I'm going to think about that compressing towards the asymptotes or away from, and I'm always comparing it actually to that 0.11 away from, over 1 away from the intersection of the asymptotes. And so because this one is closer to the asymptotes, it compresses towards the asymptotes, that means that my a value has to be less than 1. So since this has the 1/2 in front, h of x is the one that compresses towards the asymptotes. And then finally, this one again, compared to that over 1 up 1, stretches away from the asymptotes, which means a has to be bigger than 1, which was f of x. So those are really the different things we're looking at. So to summarize, if absolute value of a, if we're talking about a over x, so we're talking about f of x equals a greater than 1, then the graph is stretched from, so this is our word bank at the bottom. Stretch, I would say away from, but you can just put that from the asymptotes. And if it is less than 1, then it's compressed towards the asymptotes. And if A is greater than 0, it falls in quadrants 1 and 3. And if A is less than 0, so it's negative, it falls in quadrants 2 and 4. So that finalizes everything with the graphing that we needed to do. And now we're going to switch gears. We're going to go back to the front side of this sheet. And this side starts to talk about real-world application and modeling rational expressions. So if we read this first word problem, it says, Mary and some friends are going to rent a large car and stay at a resort for vacation. Good timing for this one with spring break coming up. The cost for the beach resort is $300 per person, so everybody pays that. And the cost of renting the car is $220. If the friends agree to equally split the cost of the rental car, how many people must go on the trip for the cost per person to be no more than $350? So when we model this, that we need to know the cost per person for the resort. Everybody pays $300 flat rate. The total cost of the rental car, though, is $220, but remember, we're going to divide that equally among all the friends. So in order to make a plan, it says create a function that takes as an input the number of people and gives as an output the cost per person, which would be a very real-world thing we'd want to do. Use the graph of the function to answer the questions. So if x is the number of people and f of x is the total cost per person, remember, it's the cost of the rental car that I'm dividing by the number of people. So I would take 220 divided by the number of people, so 220 divided by x, plus everybody pays $300, so that's an additional cost per person. So f of x equals 220 divided by x plus 300 would be a function that would represent how much I would have to pay as a single person going on this vacation. Now it does say to graph this function on your calculator, and you're going to graph f of x equals 350. So what they're asking us to do is to graph this function that we just did, and to graph f of x equals 350. And the reason for that is because ultimately we're trying to answer the question of, we want to know, remember the ultimate question up here was how many people must go for it to cost no more than $350. So I only have $350 to spend. How many friends need to come along? When I graph this in my calculator, and if you're not sure how to do that, make sure you see a teacher to get some help. It looked like this, which should make sense because it shifts 300 up, and then it shifted away from the asymptote because of the 220. And then when I graphed 350 and found the point of intersection, I got 4.4, comma 350. So which means the graph intersects between 4 and 5. So when it asks us to check, I would do f of 4, which means I do 220 divided by 4 plus 300, gives me 55 plus 300. So if 4 people go, I owe $355. And then if 5 people go, I would do 220 divided by 5 plus 300, gives me 44 plus 300, so it's $344. So the minimum number of people who must go on the trip to keep the cost less than $350 is 5 people. So I would need that 5th person to go for me to be able to afford the trip. So this is the idea of how we can use rational expressions to answer real-world examples. And I want you to pause this and try to do the next one on your own. Write the equation and figure out the answer. Okay, so the problem said Justin has purchased a silkscreen kit for applying designs to fabric. The cost of the kit is $200, and then he has to buy t-shirts for $10 each. He uses his kit to apply a design and then sells the shirts. Model this situation with a rational function that takes the input, the number of t-shirts, and gives an output, the cost to buy a silkscreen and silkscreen each shirt. We're going to use a graph to determine the number of t-shirts that brings the cost below $17.50. Okay, so when I go to write my function, again, I'm always going to have two numbers. One that you can take that cost and divide it over a bunch of things. So like in the last example, it was the car. We were going to divide the cost. Well, in this case, we only pay the cost of the kit one time. So every time I print a silkscreen shirt, I can divide that cost amongst those shirts. So I'm going to do 200 divided by X, but then plus I have to pay $10 for every single individual shirt. So this should be our equation. F of X equals X over, or 200 over X plus 10. If I want to graph it to solve this question, I would graph when does it equal 1750. When I graph that, oops, I ended up seeing this. I got 26.7, 17.5, which means that it's got to be between 26 and 27. If we do our check, I would do F of 26, 200 divided by 26 plus 10. I got 1769 per shirt. And if I do 27 shirts, I do 200 divided by 27 plus 10, and I get 1741 per shirt. So as we can see, to keep the cost below 750, I would need 27 shirts. Now we've been asking you to solve it graphically, but before I sign off here, I do want to show you that this is a problem that you could just solve algebraically for X. I would subtract 10 from both sides. I get 750 equals 200 over X. Now because the X is in the denominator, I'm going to get rid of that fraction by multiplying both sides by X, divided by 750, and you'll see that I get X equals 26.7. So I get that same answer whether I solve graphically or algebraically, and sometimes I think solving these algebraically is just as easy. But you would have to sell 27 shirts to keep the cost below $15. So again, that's a real-world application. Today's lesson we looked at, modeling real-world application with these types of equations, and then also graphing when A is negative. Thank you.